Hi guys, this is James Boyce for RL Education. Today we're going to be looking at motion on inclined planes and how to calculate the net force of a block on an inclined plane. So normally when we add up the net force, we're just adding together all of our forces. It's as simple as net force equals force 1 plus force 2 plus any other number of forces we have. Doesn't really matter, right? However, this is usually very easy for us because all we're going to have to do normally, or in our most basic problems, is go, okay, got a block here, gravity is acting down, the normal force is acting back up, and then these two are in opposite directions. So one of them will be positive, one will be negative, and they'll perfectly cancel out. Or if the normal force is bigger, you'll have a little bit left over going up. If the gravity force is big, you'll have a little bit left over going down, or something similar. You know, you have sideways forces again, but they're opposites normally. However, in this case over here, we're not going to get opposites, okay? What we're going to get instead is a gravity force that goes straight down and a normal force that has to act opposite to this surface here, okay? So the normal force has to act against a surface. And if you just think from the perspective of this problem again, you can kind of see why that has to be. If you had a force coming out like this from a normal force off the table, right, this would lend your net force pointing slightly to the left in this example, and then the block therefore would have to be accelerating to the left. But if you just leave a block on a table, obviously the table itself is not just going to push it to the left if it's flat, right? And similarly here, you know, the normal force is going to have to act against this surface, which means it's going to have to act out in this direction here. But in that case, that actually will be off to the left, and so the block will get pushed down the inclined plane to the left, which is obviously what we expect, right? So in this case, the forces here actually look like this. This one coming down, this one coming against this surface off to the left. The question for us now is, okay, how are we going to add them up? What is it going to look like when we do add them up? And that's what we're going to get into now. Okay, so the first thing we're going to look at is how to actually add these forces up. And to do that, I'm just going to move them across over here so we have some space to work with. Now, the first thing to notice is that when we drew these forces, we drew them from the middle of the block and then, you know, in the direction they were pointing. However, when you want to add up vectors, hopefully you know this from math, you need to add them top to the tail. At the moment, everything's coming from the center, whereas we need them to look like this. So that the end of this vector here points down to the beginning of this vector here, and it shows us the direction that they are overall both going. Now we've got them like this, we can add them up. We can see that if we start here with this force, go down, we get to here, this brings us to the beginning of the other force, comes back up, goes to here. The overall journey has gone from here to here, and so therefore, our overall force is just going to look like this. Now, if we bring this back over to the block where we had it originally, those forces now look like this. Again, don't draw them like that on your block, but just for the purpose of example, that's the effect they're having on the block. And then this net force looks like that. And as we can see here, it's a bit messy, but the important bit really is that this net force, the blue one, is pointing down the inclined plane. And that's what we're going to expect. That's what we should expect. That's what we know from real life that we do see. We see this 5 kilogram block just slide down this plane, okay? And the only question we have to ask ourselves now is, how big are these forces? What are they all? So I've redrawn these forces slightly bigger over here, so we have a bit more space to work with. The first force to work out is very easy. We've just got gravity force straight down. We know that gravity force is always just going to be mass times the acceleration of gravity. In this case, it's just going to be mass of the block you're working with times g newtons, and that's it. However, for the other forces, we need to work out what angle they're coming off this one at and how big they need to be. Now, luckily for us, we can see that this matches up with the triangle we've already got over here, right? We've got this net force, which just goes straight down this plane, and we've got this normal force here, which has to be coming directly off this plane, which means that these two here are at right angles. This one goes straight down here, and the normal force straight up here. Therefore, we can jot in right angle right here. Once we have this, we can work out all of the angles in this triangle. We've got this one up here, where straight down, which goes along with this side here, meets the net force, which goes straight down this side here. Therefore, this angle in the main triangle is equivalent to this angle between all of our forces. And then similarly, they all add up to 180. This is 90 degrees, this angle, 90 degrees, this angle. Therefore, this last angle here must be this last angle here. And so we can put that in as well. We've got one here is equal to that one there. And so now we've worked out all three of our angles here. We've got a right angle triangle. We can just use SOHCAHTOA to work out all of our forces. We've got the adjacent force to this blue angle, which is one we'll typically use because it makes this angle here, 30-degree rise on this plane. The normal force down here, because it's adjacent to this angle here, we get that this side length will just be mg cos of this angle here, which in this case is 30 degrees, so we'll call it 30 degrees. For this angle here, this is the opposite to this 30-degree angle here, and so we know that this side is going to be mg sine 30 degrees. This one in blue. Like so. And so these here are all the forces you need. The gravity force is always going to be mg. The normal force for an inclined plane situation will always be mg cos of this angle here. And you know that the net force for an inclined plane situation will always be mg sine of this angle here, where mass obviously given by this block resting on the plane. Therefore, for the example we've been given in this video, our net force will just be m times g, 5 times 10, times sine 30. Going to be 50 for 5 times 10, and sine 30 is just equal to a half. 50 times a half is 25 newtons. Therefore, we have net force on this 5 kilo block of 25 newtons going down this way. And then therefore acceleration of a 5 kilogram object being pushed with 25 newtons of force is just 25 divided by 5, or 5 meters per second squared. Now for homework this week, what I want you guys to do is try this problem. We've got 20 kilogram block on a 45-degree incline, 7 meters from the bottom of the inclined plane. First thing I want you to find is what is the normal force on the block. Second thing I want you to find is how long will it take the block to slide to the bottom of the inclined plane. Best of luck, and remember to leave any questions or comments you had about this video below.